I'm Shahbaz. Today I'm going to talk about our work on, like what Ben mentioned, source-routed multicast for public clouds. It's a joint work with folks at Stanford, Princeton, Technion, and VMware. So in this talk, actually, I'm going to show you like how we scale multicast in public clouds by exploiting different domain-specific characteristics of multi-tenant data centers and using programmable data planes, both software and hardware. So this talk is going to be more like an application of OVS along with some other hardware switches to scale something that right now no public cloud is providing to the customers. So before I move on to the technical details, so typically cloud workloads are driven by systems that deliver large amount of data to groups of endpoints. And in cloud providers today typically host hundreds of thousands of tenants, each of which may run tens of hundreds of such workloads. And examples of such workloads are streaming telemetry, where hosts are sending telemetry data to groups of collectors, replication for databases and state machines, distributed programming frameworks like Hadoop and Spark, and then finally like publish-subscribe systems for sending data to multiple receivers. And in the very end, like infrastructure applications like VMware NSX, where you are running on top of a provider and you need to replicate broadcast, unicast, and multicast traffic for multiple tenants or clients. And then there can be many more that people are coming up with. So the thing is, if you look at these workloads, it makes natural sense to have multicast to support these workloads. However, none of these cloud providers today, like typically Amazon, Google Cloud, and Microsoft Azure, support native multicast in their data centers. And I think the reason why they are not doing so is like there are typically many different things that they need to provide in the data centers. And these existing sort of multicast applications are limited in one or many ways. And that's why they become infeasible for cloud deployments. So control overhead is one thing, tenant isolation, bisection bandwidth, and the ability to run at line rate. So they need a bunch of these properties in any multicast implementation to be able to be deployed in a cloud setup. So for example, if I talk about IP multicast, like IP multicast has faces a lot of control plane issues in terms of scaling under membership churn. It's limited in the number of groups you can support, and also it cannot fully utilize the bisection bandwidth in multi-tenant data centers. SDN-based multicast solutions help alleviate some of the control plane issues, but are still limited in the number of groups that you can support. And then there are techniques like flow aggregation, where they try to aggregate flows for multiple tenants together, but in that case, you do get more groups, but then you are limited by either low bandwidth utilization or you don't provide tenant isolation and so forth. So at this point in time, application layer multicast is like one of the gold star methods of doing multicast in public clouds. But the thing is, like with these approaches, there's a huge redundant traffic overhead because you're opening up unicast connections to all your receivers and sending the same data across all of them. There's a huge CPU load overhead. And also, like these approaches cannot run at line rate. And because of these limitations, many certain classes of workloads, like workloads for financial applications, cannot use the existing public clouds for their applications. And then there are some other schemes based on source-routed multicast, like SDM and Beer. One of the key issues with them is like the sizes of the groups. So even though they can support many groups, but the sizes of these groups are usually limited. And also they cannot run at line rate for larger networks. So the reason why I'm telling you about all this is like, if you want to provide any multicast support in such like large-scale public clouds, you need to be able to support all these different factors in your implementation. And with Elmo, what we have done is like we have tried to come up with such implementation which tries to address all of them. Pretty much tries to give you the best performance across various factors with some control plane overhead, but not that much, and with some traffic overhead. But again, it's pretty. If you look at the plot here, like it's pretty low compared to other implementations. So what is Elmo? Elmo is again a source-routed multicast implementation for supporting multicast in the public clouds. What happens in Elmo is like a software switch sitting at the hypervisor host receives a packet, and then it encodes the multicast policy inside that packet. The packet is then sent out to the data center, and the intermediate switches, the network switches sitting in the data center, read this policy and then route packets to the receivers participating in that multicast tree. So that's the basic implementation. There are software switches encoding the multicast policy, and then there are hardware switches. Again, these are programmable hardware switches, not the typical Cisco switches or fixed function switches. So collectively, these two help us to build an implementation which is scalable across different vectors. So if you look at it closely, there are two main challenges in implementing this approach. One is how you efficiently encode this multicast policy inside packets, and the second is how you process them at line rate. So if you look at the data centers today, they tend to be very symmetric. Like the topology, they have a layered structure in their data center topologies, like with core layers, spine layers, and leaf layers. And also there are a limited number of switches across any path. Like for example, in this case, there are if you go all the way to the core and come back, there are 5 switches that you see in the middle. And then finally, in order to keep the internal bandwidth use or minimize the internal bandwidth use, the tenant VMs tend to be clustered together into some part of the topology. Like they're not spread across the entire data center. So in Elmo, what we do is we exploit these properties, and we come up with an efficient encoding that we encode in the packet, and then to process it at line rate, we use programmable data planes. So there's a P4-based implementation of OVS, which was our prior work. We use that as a hypervisor switch. And then we use Barefoot Tofino or X-Client switches in the network to read the policies that are encoded in the packet. So moving on to the actual design approach, so how do we encode the multicast tree in Elmo? There are 5 key design decisions. And I'll go through them one by one using the following example. So this is a typical data center. We have some VMs sitting under the host 1 and the last host, host 4. And the dotted lines here, if you can see them, they show the ports in the data center that are participating in the multicast tree. So moving on with the first design decision, what we do is we encode all the downstream ports in these of these network switches using a bitmap. So what it tells us, if you look at the core switch at the top right, at the top left, 1011 means that the packet, if any packet comes to this core for a particular group, it will go out to these three ports that are defined by 1 in the bitmap. And the reason why we do this is because bitmap is an internal data structure that switches use for directing packets to multiple ports. And also, based on the co-location and placement of the tenants in the data center, either all the ports, many of the ports are participating in the multicast tree, or none of them. That's what we have seen. And then when going upstream, what we do is we use a flag bit that specifies the switch if that bit is set, then use the underlying multipass policy like Conga, ECMP, or Hula to route the traffic upward. So this is how we sort of represent our multicast tree using bitmaps. So next, to further reduce the number, so this is one way. But if you look at this thing, collectively, this can become a huge packet. If you collect all these bitmaps together and try to encode them as a packet header, this can become pretty cumbersome. So to reduce this, the second sort of design decision that we make is we exploit this sort of symmetry in the data center topology. We see that if you look at all the core switches, they're using the same bitmap. And similarly, all the spine switches in the pods are using the same bitmap. So we define them as a logical switch, and then only keep one bitmap for all of these switches, and along with the switch ID. So instead of having a separate switch ID for S0, spine switch S0 or S1, we just define that as a pod P0, and then have a single bitmap corresponding to that pod. Again, to further reduce this, it can still be very cumbersome. So moving on to further reduce this, what we do is we allow different switches on the same layer to share a bitmap. So for example, in this case, we can have L5 and L7 share a bitmap. So this combined bitmap is a bitwise OR of their independent individual bitmaps. But in this case, you can see both of these switches will send one extra packet. For example, L5 will send an extra packet on the 4th port, and L7 will send an extra packet on the last port. But this is allowable. If we want, so there's a trade-off here. If we want to reduce the number of bitmaps that we want to encode in the packet, we have to sort of allow some extra transmission. And we will show, even if we do allow 12 or more sort of extra transmissions, the overall overhead compared to overlay, multicast, or unicast based multicast is still very, very small. Moving along, so again, just to point out, like this combination like of switch IDs and bitmap, we call this a P rule, which is a packet rule, meaning that it's installed inside the packet. And then to find out, so we implemented a clustering algorithm to find out, like, which is a greedy version of min-k union to determine which switches should share a bitmap so that they yield the minimum number of extra transmissions. So this is sort of like an optimization for us. Like for each layer, we run this algorithms to find out, like, okay, which of these switches should share a bitmap so that the overall extra packets that we are sending in the network are minimized. Moving one step further, the thing is, like, even after applying all these techniques so far, we may still have some leftover switches. And to handle those leftover switches, we sort of come up with this notion of a default P rule. So what this means is, if we only have one P rule space in the packet, then L5 and L7 will get a P rule, but then still we have L0 and L6 remaining. So what we do is, like, we take these two, and then we define, like, put them together in a default P rule, which is like a bitwise OR of all the switches that are not assigned a P rule at this point. So up until this point, we can take any multicast tree, and using these techniques, we can encode them in a packet header. But the thing is, like, if you go with the default P rule scheme only, in the limiting case, this can lead to a lot of traffic overhead. For example, there are many switches there are some switches that are left at the end. You take them together, you do a bitwise OR, then eventually what happens is, like, maybe you will end up with a lot of bits set in those bitmap. So essentially what you're doing is, like, you're doing a broadcast across all the switches that are assigned to assigned to the default P rule. So again, here what we do is, like, we come up with this neat trick. We say, okay, if we want to reduce the traffic overhead without increasing the packet header, what can we do at this point? Well, we know that these switches already have a group table supported in them. So here we use these group tables as a sort of a cache. We say, like, okay, first of all, before assigning any switch to the default P rule, see if there is a space for a group table. And if there is a space in the group table, then install a rule in the table, and then only assign those switches to the default P rule that have no group table space available to them. And this way, what you can do is, like, you can reduce this sort of extra transmissions happening based on the default P rule. So these were the, like, 5 key design decisions that we used, and collectively they allow us to, just to point out, like, we install an S-tool entry at this point. And then these are the techniques that we use to collectively come up with a multicast encoding, utilizing packet headers, as well as some state in the switches. And then if we look at this example that we have, if we assume that the sender is sitting under L0, and we have only one P rule per downstream layer, like for spine and leaf layer, and we only allow 2 extra transmissions per P rule, and we don't have any S rules, then what will happen, like the encoding for this design will look like the following. The packet will go out from sender to leaf L0. It will see we will get the following, so we will get the following bitmap. This bitmap specifies in the upstream direction when the packet is coming in from here, use this bitmap to send any packets down participating in that tree from L0. And if this bit is 1, then you have to multipath that packet upward to the spine layer. And then we move on to the spine layer. At this point, we have only one setup as a flag bit, and these 2 bits are 0 because there is no layer participating in the downstream direction. And then moving on, using this bit, we have the following bitmap, which is specifying that at the core layer, use this bitmap to send the traffic out. So here you can see we send 3 extra packets, 3 packets from the core down to the spine layer. And then up till this point, we were only using sort of like a 1 bitmap. Like we have a bitmap here with a flag bit, another bitmap for the spine layer with a flag bit, and then finally this bitmap at the core layer. And now from there, we are going backward down to the receivers. So at this point, what we do is we define, because we only have space for 1 P rule, we assign pods P2 and P3 together as P rule, and use a default P rule to assign the remaining leftover pod P0. Similarly, we do the same thing at the leaf layer. We have leaf L5 and L7 assigned a P rule, and then L0 and L6 become part of the default P rule. If we move one step further and say, like, okay, we have a space for 1 S rule, like there is 1 group table entry available in all these switches, then what happens is, like, these default P rules are replaced with the S rule. And now, like, S0 and S1 in pod P0 have an S rule, and similarly L0 and L6 get an S rule. Next, what happens is like, so this was like how the encoding is happening. But eventually what happens is like the participants or the members of a multicast group send join requests to the controller. This controller then computes this encoding, and then it generates a Elmo header, which is like a serialized form of these bitmaps. So this is the bitmap in the upstream direction for leaf layers, then spine layer, then finally the core layer, and then in the downstream direction for spine layer and the leaf layer. And collectively, we call this an Elmo header. The controller then installs this on the software switches. It also specifies like if the packet is coming in from a VM, it specifies which output ports the packet has to go out to, like the neighboring VMs and the leaf switch. And it also like specifies when you're sending the packet out to the leaf switch, encode this Elmo header on the packet before sending it out. And then if some switches need S rules, it also installs these S rules on those switches. I'll later on point out like the key thing in this work compared to prior SDN-based work is like the number of S rules or the group table entries we are using in the switch is very small compared to the traditional approaches. And we can actually omit these S rules by just saying, just go with the default P rule. We don't need an S rule if the control plane overhead is a problem in your case. So now if the packet is coming in from a VM at this point, the PISCES, like the OVS P4-based OVS switch will take the packet, it will send the packet down to the neighboring VMs, and before sending it out to the leaf, it will encode the Elmo header on top of it. Now at each hop, that switch on that hop will see if there is a matching P rule for that switch. If there is, it will use that to send packets down or upstream. And also before sending the packet up to the next hop, it will remove those bits from the header, because none of the switches in the following path need that information. So you reduce the size of the packet as you move along in the network. And then if some switch in the hop does not find a matching P rule, it looks for an S rule. And then based on that, it routes the traffic. Or finally, it uses a default P rule to send the traffic out. So from here, you go here. Core switches will see if there is a P rule for them. Yes, there was. They go here. And now if you see, I think in pod P2, it was using an S rule. So at this point, it will simply use an S rule, but it will still drop the packet, like remove the header from the packet, because none of the following switches need that information. And by the time you reach the software switches, there is no header on the packet. Switches simply read that packet based on the destination IP. They decide which VMs in the host need the traffic, and the traffic goes out. So this is how the basic scheme works. And yeah, so this was the typical way we implemented this thing. And I'll just show you with evaluation like how we scale. So in the evaluation, we actually sort of evaluated 4 key parts. I'll just enumerate them here. One was like the data and control plane scalability, like how do you scale in the number of groups you have, and what is the control plane overhead. Similarly, what was the end-to-end application performance? Hardware resources for this, because again, we are using programmable hardware switches, so how much header space we are using, and do we have some space available for other protocols? And then finally, the load on the hypervisor switches. So for the scalability test, what we did was we implemented a typical class topology having 27,000 hosts, with each rack having 48 hosts in it. And we use 1 million groups, and we use a trace from IBM WebSphere Virtual Enterprise application to find out, like, okay, what are the group sizes? What are the typical group sizes that we need to use? And we use a packet header size of 325 bytes, which means like we can encode around 30 bitmaps in a header. So with that, what we found was like, if we don't allow any sort of extra transmissions, that means we don't allow any sharing of the bitmap, we can support around 89% of the groups by just using the P rules. We are not using any default rule at this time. But if we relax this constraint of extra transmission and we allow like 12 extra transmissions per P rule or per bitmap, then we can actually support all the like 99% of the groups by just using P rules. The corresponding sort of change in the S rule tables, you can see if we don't allow any extra transmissions, then we are using like pretty much 95% of the switches are just using less than 4K rules, which is much less than the typical SDN-based implementations by one of the papers like Lee et al. And then if we relax this constraint of like extra transmissions, then the number of rules are like less than 100 in all the switches, which is like typically we are not using any of the spaces. So again, with respect to like how the traffic overhead is changing, you can see if we don't allow any sort of extra transmissions, we are actually similar as the ideal multicast. But if we relax this constraint, we are seeing some sort of extra overhead, which is like much less than the typical cases of using unicast or an overlay multicast in this case. The next thing that we wanted to evaluate was, okay, what is the control plane overhead? Like whenever a change happens, how often the controller has to go and update the switches? In this case, what we found is like for the case of core switches, because we are already always using bitmaps, there is no S rule, so there is no update. For spine and leaf switches, the updates were like in tens of updates per second, and then hypervisor switches were seeing most of the updates. But these updates are still much less than the updates you will see even at the core switches inside the SDN-based implementation. So like it's typically on orders of magnitudes more than even the updates we are getting for the hypervisor switches. The next thing that we evaluated was the application performance. Again, with Elmo, any subscriber that was receiving packets was receiving the full line rate compared to the unicast-based approaches, because as you increase the number of unicast receivers, the throughput goes down. And the corresponding change you can see in the publisher side, like with unicast, the CPU utilization is increasing by a lot, but with Elmo, the CPU utilization at the publisher side remains the same. The next thing was like, okay, what's the overhead in terms of hardware resource requirements? We found that even using 30 P rules for a typical switch, like parsing 512 bytes, like a Barefoot Tofino switch, we only consume like 60% of the header space, and we still have 190 bytes for other protocols in the data center. Typically, they are around 90 bytes at this point in time. Okay, I think the battery issues. So in this case, we wanted to show the overhead on the software switches. In terms of PPS, we see some performance like degradation, but this is not like based on the capacity of the host. It's based on because we are adding more headers on the packet, the size of the packet is increasing, and that's why you see the drop in the PPS, but the throughput still remains the same, like meeting the line rate requirements at a hypervisor switch. But the thing is, like, we were able to achieve this sort of performance by doing this optimization in PISCES, where instead of thinking of these P rules as individual bitmaps, we combined them together into a large chunk and then just used one write DMA call for writing the packet, like writing the data on the packet. But if we did like individual write sort of calls for each P rule header, we found that as you increase the number of P rules, the throughput started to degrade, tapering off at around 5 gigabits per second with 30 P rules. So instead of like doing independent write calls, we just took it as a bunch and did a batch write call on the packets at the software switches. Okay. So in conclusion, I just wanted to mention, like, we presented Elmo as a scalable multicast service for public clouds, designed to be deployed in multi-tenant data centers today. And in Elmo, the Elmo itself like generates an efficient encoding of the multicast policy for the switches to use, for the programmable switches to use at line rate. And then with that, I conclude my presentation and happy to take any questions.
Let's thank our speaker. We ran a little over, but if anybody has a question, we have time for one.
Yeah.
Hi. Were the subscribers using a protocol to subscribe to the multicast trees, or were they just being set up by the controller?
So the subscribers, they are sitting in the tenant domain. They talk to the controller through an API to ask for, like, okay, we want to join a particular group. And through that API, the controller will then generate the underlying encoding. So that, like, the encoding and everything is happening in the provider domain. The subscriber only specifies that I want to join this group. And in the provider domain, they just see the traditional UDP or TCP interface. There is no change in their interface that they use.
Okay, thank you.
To talk.
All right, let's thank our speaker one more time.
All right, thanks.